Hello everyone, today we're talking about the real zeros of polynomials. So when we were doing the section on graphing, remember the zeros were very important to determine what the graph is going to look like. So here we're actually going to be able to determine the zeros of third degree, fourth degree polynomials, stuff like that. So the first I want us to find all the rational zeros of this given polynomial. So how we start? I've got my p, and this p corresponds to whatever the constant is. Doesn't matter if it's positive or negative. So the p is whatever the constant is, regardless if it's positive or negative. You'll see why in a second. The q is whatever comes before my leading coefficient. So whatever the leading coefficient is, in this case, it's 1. So then to find all the possible zeros, this is what I'm doing. I'm trying to find all the possible zeros that could make this cubic equal to 0. So I take all the factors of p, right? So I take the factors of p meaning 1, 2, 3, 6, 9, and 18, and I divide them by all the factors of q. In this case, just 1, because 1 is just a factor of itself. So what that looks like is I take my factor of 1 divided by 1, and it can be the positive or negative of that. I take the 2 divided by 2, divided by 1. Could be the positive or negative of that. Okay, then I take my 3 divided by 1, could be the positive or negative of that. Right, then I take my 6 divided by 1, could be the positive or negative. Then I take my 9 divided by 1, could be the positive or negative. And then I take my 18 divided by 1, and that could be a positive or negative. So the reason why I divide them all by 1 is because 1 is only a factor of itself. And you'll see in the next example when we have a number that has more than one factor. So this one's just dealing with when we have p is our constant, multiple factors, divided by q that only has a factor of 1. So if I simplify real quick, I get my factors of plus minus 1. I get my possible zeros, as you say, not my factors. My possible zeros, plus minus 1, plus minus 2, plus minus 3, plus minus 6, plus or minus 9, and plus or minus 18. So now I'm just going to start going through all the possible zeros and seeing which ones make the polynomial equal to 0. So I'm just going to start at the first one, and 1's the easiest one. That's why I typically start at 1. So I'm going to go through and I'll plug a 1 in wherever I see an x. So p of 1. I don't have room here, so if you don't remember the equation, you can go back up, copy it down, and then follow along with me. So p of 1 is 1 cubed plus 4 times 1 squared minus 3 times 1 minus 18. So here I've just gone through and plugged a 1 wherever an x was, and that gives me a value of negative 16. Not equal to 0, so 1 is not a factor. Alright, I'm going to switch colors because it's starting to run together. So then I'm going to do, so positive 1 didn't work, so now I'm going to try negative 1. So p of negative 1, and I take and I plug a negative 1 in wherever I see an x. So negative 1 cubed plus 4 times negative 1 squared minus 3 times negative 1 minus 18. And when I do that, that gives me a value of negative 12. So still not equal to 0. So negative 1 is not a 0 of the polynomial. All right, so then I'm going to move on to 2. The positive 2. So I take p of 2. So I take 2 cubed plus 4 times 2 squared minus 3 times 2 minus 18, and that gives me a value of 0. So here I have found my first 0 is a positive 2. So plug a 2 in this equation, I end up with 0. So that really means that the factor of that polynomial, right, is x minus 2, right? That's the factor of that polynomial. So now that we know the factor, in order to simplify our polynomial down to try to narrow it down to the zeros, I need to use synthetic division to divide the original polynomial by the number that we now know to be its factor. So, to do that, if we remember, I get x cubed plus 4x squared minus 3x minus 18, and I need to divide that by x minus 2. So this division is completely new to us. We're actually going to divide polynomials. So, we're going to do this using synthetic division. How synthetic division works. Whatever my 0 is, so my 0 in this case would be a positive 2, because 2 minus 2 makes the 0. Whatever my 0 is, I plug that in. And then inside, so this is kind of like long division like we learned in elementary school, right? So inside my division, I'm going to plug in just the coefficients of my polynomial. So 1, 4, negative 3, and negative 18. All right, so then I start, carry down my 1, right? And then, so 2 times 1 is 2, 4 plus 2 is 6. 2 times 6 is 12. Negative 3 plus 12 is a positive 9. 2 times 9, 18. Negative 18 plus a positive 18 gives me 0. So this proves again that 2 is a 0 of this polynomial. And what this leaves me with is x squared plus 6x plus 9. So that leaves me with x squared plus 6x plus 9. After I divided by the factor x minus 2. So now I'm left with the quadratic, so I can simply factor it, and it factors to x plus 3, x plus 3. Okay, so giving us all of the factors of the original polynomial to be, I'll write this in a different just to distinguish, the factors of p of x is x plus 3, x plus 3, x minus 2. So the question asked for the zeros. So the zeros of p of x are negative 3, multiplicity 2, and x minus 2, so positive 2. So remember, since we have two x plus 3's here, that means our 0 is going to have a root, so that means our polynomial is going to have a root of negative 3, and it's going to have multiplicity 2. I'm going to show you the graph real quick to show you again what I mean by that multiplicity 2. So here I have it graphed. And we can see that at negative 3, right, I'm going, and then I don't cross the x-axis. I actually just touch the point, negative 3, 0, and then I start going down again. So when we just come up and touch the x-axis, that's what it means to have a multiplicity 2. Okay, so if we're trying to sketch them just by hand without looking at the calculator, when we see a multiplicity 2, we know that yes, it is a 0, but it's not going to cross the x-axis at that point, right? It's just going to go up and touch it. And then from the graph, just a couple things to review. We can see our y-intercept is negative 18. And then our other root, our other 0, is x is a positive 2. So since this is a third-degree polynomial, right, and it's positive, starts left, ends right, and we can get our x and y intercepts with multiplicity 2, and we can sketch this graph pretty easily without our calculator. So let's do another example. Now a fourth-degree polynomial. So again, we start off with p and q. My p in this case is 4, and my q is 2. Oops, I wrote p. So, all the factors of 4, 1, 2, and 4. All the factors of 2, 1, and 2. So now when I go and list all of my possible zeros of p divided by q, I have to take 1, 2, and 4 divided by 1, and then 1, 2, and 4 and also divide it by 2. So my possible zeros or p over q, it's going to be plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 4 over 1, and then now I have to go and I have to do plus or minus 1 over 2, plus or minus 2 over 2, plus or minus 4 over 2. So plus or minus 1 over 2, plus or minus 2 over 2, plus or minus 4 over 2. So now I'm just going to simplify a little bit. So 1 over 1 is going to simplify to plus or minus 1. Plus or minus 2 over 1 is going to simplify to plus or minus 2. Plus or minus 4 over 1 is going to simplify to plus or minus 4. Plus or minus 1 over 2 isn't going to simplify, so it's just going to stay plus or minus 1/2. And then since 2 over 2 reduces to 1, I don't need to write that one again. And since 4 over 2 reduces to 2, I don't need to write that one again. So here are a list of all of my possible zeros. So now, just like in the last one, I'm going to go through and start plugging in until I get a 0 for my polynomial. So the first one I'm going to start with is the smallest zero, so positive 1/2. So p of 1/2, I'm plugging the 1/2 in. That gives me 2 times 1/2 to the 4th, minus 7 times 1/2 to the 3rd, plus 3 times 1/2 squared, plus 8 times 1/2 minus 4. So if I simplify just a little bit, this gives me 0.125 minus 0.875 plus 0.75 plus 4 minus 4. And if you compute this, you actually get that this is in fact equal to 0. Meaning 1/2 is a 0 of my 4th degree polynomial. Right, so that is a root. So now that I found my first 0, I use synthetic division, divide through. So I can see what I am left with after I divide by that factor. So remember that the fact that 2 is a 0 means that the factor is x minus 1/2. So I'm really taking my 4th degree polynomial, I'm dividing it by x minus 1/2, and that gives me 1/2. It's positive 0. And I just put the coefficients of my 4th degree polynomial in there. So 2, negative 7, 3, 8, negative 4. So then use synthetic division. Let's see, carry my 2 down. 1/2 times 2 is 1. Negative 7 plus 1 is 6. 1/2 times 6 is 3. This should be negative 6, right? A negative 7 plus a positive 1 is negative 6. Times 1/2 is negative 3. So 3 plus negative 3 is 0. 1/2 times 0 is 0. 8 plus 0 is 8. And 1/2 times 8 is 4, giving me remainder 0, proving that 1/2 is a factor of that 4th degree polynomial. So what does that leave me with? It leaves me with 2x cubed. Remember, I started with a 4th degree, so when I divide by that factor, I'm going to be left with a 3rd degree, minus 6x squared. Next, I have a 0 for my x term, so I do not include an x term. I go straight to my constant of 8. And then remainder 0, so this is what I'm left with. So now I've done all that work to find the first 0, divide the polynomial by the factor, x minus 1/2, and now I'm left with a 3rd degree polynomial. So again, I've got to go through, plug the possible zeros in, and the original zeros are the only ones we have to worry about. We don't have to find new zeros. So go ahead and go back to the original zeros, plug them in, and see if we can find another 0. So I tried -1. So this is p of x now is equal to that. So I tried -1. So -1 gives us 2 times -1 cubed minus 6 times -1 squared plus 8. So that's a -2, -6, +8 gives me 0. So -1 is again a 0 of p of x of our original 4th degree function. So since -1 is the 0, that means we get the factor x plus 1. But I have to use synthetic division, divide by -1 to get down to a quadratic where I can factor. So -1, I want to use a different number, so I can different colors so I can separate. Then just the coefficients of my new 3rd degree, because I've divided by a factor already. I don't have to go back to the 4th degree. So my coefficients are 2, -6, 0, and 8. Carry my 2 down. -1 times 2 is -2. -6 plus -2 is -8. -1 times -8 is a +8. 0 plus 8 is 8. And then -1 times 8, -8, giving me a remainder of 0, proving again that -1 is a 0 of that polynomial. So now I've got 2 zeros. I've got x. I've got 2 factors. X plus 1 is a factor. X minus 1/2 is a factor. And then I'm left with the quadratic 2x squared minus 8x plus 8. And this factors to 2x. So 2x minus 4, x minus 2. That would get us back to this quadratic, meaning my zeros, right, set 2x minus 4 equal to 0. Add the 4 to the other side. So my zeros in this case, both 2, right? If I plug a 2 in here, I get a 0. Plug a 2 in here, I get a 0. So my factors of my polynomial are 2, I should say, p of x. All the factors include 2x minus 4, x minus 2, x plus 1, and x minus 1/2. Okay, so those are my factors of that polynomial. But again, the question asks for the zeros. So that gives us +2, multiplicity 2. -1, +1/2. Okay, so we've got 4 zeros for a 4th degree polynomial, right? Always going to be the case. That may not always be real zeros, but we're definitely always going to have 4 zeros. So again, I'm going to show you the graph of this function real quick to show you what that 2 multiplicity 2 looks like. Okay, so here we can see on our graph, we get the y-intercept of -4. Okay, so it's going to cross at -4. It has a 0 at -1. It has a 0 at +1/2. And then at +2, you can see how it comes down and just touches the x-axis, doesn't cross it, and goes back up. So again, since this is a 4th degree polynomial, right? Even degree means, and even and positive means our end behavior are both going to go to positive infinity, right? We can get our 3 zeros, one with multiplicity 2, and we can get our y-intercept and draw this graph pretty well without our calculator. And finally, let's go to the last problem. They just want us to show that A and B are lower and upper bounds for the real zeros. I'll get it out. So what is important about this is, if I know the zero, if I know negative 3 is a lower bound, and I know positive 2 is the upper bound for the zeros, then I know that my zeros are going to fall between those 2 points. So if you have a whole lot of p divided by q's, a whole lot of possible zeros to check, this might be beneficial because then you know the zeros fall between negative 3 and 2. So it would help us narrow down our possible zeros. So in order to prove that these are the lower and upper bounds, first I'm going to take my polynomial and divide it by my 0 of negative 3. So again, synthetic division, carry down my 8, that gives me negative 24. 10 plus negative 24 is negative 14. Negative 3 times negative 14 is a positive 42. Negative 39 plus 42 is a positive 3. And then negative 3 times negative 3 is a negative 9. 9 plus 9 is 0. So just so happens that the negative 3 is a 0, but also it is a lower bound because my signs alternate for each entry. So it's a positive here, negative here, positive here. 0 shows it's a root, so we're done. Our only 3 entries are here. But if there were another entry here, then this one would have to be negative. And if it were positive, negative, that would mean it's a lower bound. My zeros all have to be greater than or equal to negative 3. Okay, then to prove that 2 is an upper bound, we do the same thing. Okay, so we carry my 8 down. 2 times 8 is 16. 10 plus 16 is 26. 2 times 26 is 52. 39, negative 39 plus a positive 52 is a positive 13. Times 2 is 26 for a positive 28. So, different than proving it's a lower bound, to prove it's an upper bound, all of my signs must be positive. So since all my signs are positive here, I know that my possible zeros are 2 or less. So they're equal to or less than 2 because here all my signs are positive. So to prove it's an upper bound, all the signs must be positive. To prove it's a lower bound, the signs must alternate. Positive, negative, and if we had another one, negative, positive, negative. Depends on how many degrees of polynomials we're talking about. All right, so that's it for finding the real zeros of polynomials. So doing that will give you all of the points that fall on the x-axis. So go ahead and try the example problems that accompany this on the PowerPoint, and we'll talk about them in class tomorrow.